Good day everyone, welcome to another session for manufacturing. This will be lecture session number 22 for MGC 110, and it will be lecture session number 6 for manufacturing section of the module. Today we are going to be dealing with a different section, as we will be touching on a different type of manufacturing procedures. So previously we dealt with casting, and then we dealt with metal sheet working. Now we are going to machining. So the general description of machining operations can be put as follows. Machine operations involve various processes in which a piece of raw material is processed accurately into a desired shape and size by means of carefully controlled material removal process. Usually a form of cutting is used, and maybe just to add here, and rotation. So we will deal with both. So there is a removal of material by using rotation. We will see which type of materials requires what, but machining operations is those operations which we form shapes by removing the material that we need from a block of material or a raw material. Usually they come in terms of blocks, circular blocks or square blocks, but we will remove and cut them to shapes that we are looking for. The geometry that you are looking for determines the type of a machine that you will be using in order to produce that geometry. We have 3 of them that we are going to discuss in MGC 110. That will be turning, milling, and drilling. So turning, milling, drilling, or boring. But boring is we're going to touch it in this session when we are discussing turning, but it's a method also of making holes, but we will see why it is a little bit in the gray area. So just keep that in mind so it doesn't have to confuse you. Turning is applied when you have to produce circular shapes like cones, any circular shape that you can look around. Usually hard materials will be used during this process. Milling, if you want any other shape, square shapes, rectangular, planar shapes, or linear components. And then drilling is another method which we can use to make holes, usually making holes on all type of products, either coming from turning or milling, but it's used for making holes. But all of them involves removing material in order to get a shape that you are looking for. The history, you can just go and find out about the history of machining operations, where they come from, but you are going to find that they link more or less to the industrial revolutions. So you are going to find what led to what, and what manufacturing procedures were used, and what manufacturing procedures were required and ideal for that particular time. Just go and find out about that history. You will find the early days methods where this was used as a drill. It was a very clever method of that time. It is still a very clever method even today, because it kind of helped us to build more onto the idea up until what we have today. So this is mechanical work. Linear mechanical work is converted to a rotational mechanical work. So just remember this. Even on this side, remember that we are usually just improving and to make our life easier. That is the idea behind industrial revolutions, but we really don't know what the revolution is going to lead to. What we are aware of is that we are currently looking for methods to make our lives easier. So we are currently just looking for methods to make our lives easier, and we are improving on the methods that we found, and we are improving on the methods that we are currently using. Look into this few YouTube videos, and you can even go extra and find out using other videos, of course, just to see what operations are we going to cover, and then have a visual perspective of what we are dealing with. In campus, you can find this in our workshop, mechanical workshop. All these machines that we will be discussing, you can find them in our workshop. Turning operations, that is the topic for today, for this session. So turning involves a manufacturing procedure which a component is operated through rotation and through cutting. With turning, usually you will have I think it's worth noting at this point that you will also find in today's applications more advanced procedures which we can refer to as thinning, but they all root from same idea. They all root from the idea that we just saw, used as a method of converting a linear motion into a rotational motion. They all are derived from that. But really what is happening with thinning, fundamentally, this is a basic a machine which is used for turning. You have a spindle there which is rotating. In here I can only assume you have a lot of gearboxes, reduction, and all those. These are speed controls, these are feed controls. The feed control here is linked to the carriage here. The tool carriage moves linearly in and out. You can also have it moving in this direction, so you have the movement there. Let me just try this. The movement there will be in this direction. You can also have it moving in this direction. There you are going to put your tool, cutting tool. That's how it fits. And then you have a tail stock. This is a stock, just we use it for balancing out. You can imagine if you have let's say you have a long material that you need to operate, circular material, and you are holding it only on this side with the spindles on the spindle side, and then you are rotating this, and then it doesn't have balance this side. This thing is going to wobble and it's going to get out of control. So here you're going to find, while here the rotation center will only have one rotation center at the beginning here, while the rotation center will only have a center 0 with no displacement in the radial direction. Here, this part of the component, you are going to find a bigger rotation, so you want to balance it out with a tailstock so that it can remain concentric and during rotation. Even though we use the tailstock, sometimes during operations we find that indeed this thing is rotating out, so you'll find that it does this, but not that you are going to be able to observe this. But this is typically, it will be in small scales, microns type of errors, millimeters, but it's there. You will see it sometimes on the products that you manufacture. We have a bed. This is just where everything is grounded to. The bed will be grounded to the ground of your workshop in this case. And then you have ways. This is where the carriage, it's like a rail. This is where the carriage moves. This is the actuator of the carriage with this lead screw. It's threaded, it's a screw, so it can transmit power. Therefore, in the case that this thing is not attached to anything, it will be able to move up and down. That's how it fits. So it can feed in this direction, it can feed in that direction, X and Y. X, Y. Okay, speed controls, that is the selection of gears so that this can rotate quicker or slower. Feed controls, to control the pace at which the carriage is feeding the tool. The tool will be cutting the components that is being manufactured. A typical machine that we have in our workshop, this is the biggest one we have, manual, still doing the work. This will be the carriage here. So you can see this one ranges, it's quite a long range here. For this one, have a range which can go as far as roughly around 2 meters. So this is quite a range. And then this is the control of the feed, and then this will be your table which can feed. So you can see that it feeds one, this will feed, and then you have this small feed which feeds in and out of the picture, and then you also have this small feed here which this is more accurate, which feeds in this direction again. And then we have here the spindle. The gears are controlled by this. You will have more sophisticated methods and machines today, but they all build up from what we previously used. A more recent type of lathe, same one manual, but a smaller one, more recent with the controls over there. This is just digital or display. Here you still have controls, and then the bed and the spindle. Here is the light in case you work at night or when you need to be very accurate, so you need to see. This is the tailstock to balance out. You can see the center of the tailstock is on the same height with the center of rotation there. Otherwise, workshop is open, you can go there arrange up with the instructors in there, and then you can look and see them. At some point in your academic career, you'll be able to use this. You are going to be taught, so you also have a tailstock there. Specifications for a lathe: swing, maximum distance between centers, and spindle bore. So this is the how big you can hold a part. So sometimes you want a small one, so you're just gonna have a small spindle, and then sometimes you need a big one for bigger materials. Say you want to operate on something that is about, let's say, 30 centimeters diameter. Sometimes you just need to operate on something that is about 5 millimeter diameter. Then you have maximum distance between centers. This is between the spindle and the tailstock. That is the one that I said previously. You can find something like close to 2 meters in our workshop or around there. But that is if you need, sometimes you just need to manufacture small components like 30 centimeters length. Sometimes you need very long components like 2 meters, 3 meters, depending on the size. That will come up with this. The longer they are, the diameter is going to increase, because you don't want to have a long component and then when you rotate it's going to wobble and dance around. Don't want that. So even with this method, we still have to balance them out if they are very long. So if you have a spindle this side and then you have a tailstock this far, if it's very far, 2 meters, maybe at 1 meter you want to put another supporting component. This will be a support with rollers to allow this thing to rotate. This will be your tailstock. A swing, the distance that the cross slide can move perpendicular to the rotation. That is the, let me just go back so that I can show you the swing. This is the swing, moving in and out. If you are dealing with something that is 30 centimeters, you want to be able to work on this part in this direction, but because this is rotating, you only need to go as far really as to the center, or just past as the center of the spindle, because you can always rotate it to bring it on this side. So you can just be here and cut the whole diameter, because it will be operating, your part will be operating, rotating. You can just bring it there, your component will be rotating. This is where everything is happening on this picture. You have a tool. This is a linear moving tool. It's going to be attached to the swing, this part here. On the lathe that we looked at, this part, that's where you attach your cutting tool. It is not stationary, it only moves linear direction, back and forth, in and out of the page. That's where you attach the tool, and then you have here your component. This is your component. I suggest by the time you actually go through with this, you should have watched maybe the videos. They will make it easier for you to understand what I'm speaking about. The material specifications and selection for these tools and teeth depends on the material that you will be operating on. So that is your spindle. That's where you put your component. Component, circular, in the spindle, held by jaws. You'll see what jaws are. Operating tool comes in linear direction. Once it's feeding, when you're doing the cutting, it will produce something with this type of lines. Depending on the surface finishing that you are looking for and the hardness of the material that you are cutting, you will control that, controls your feed. The calculations you're going to perform them in this session for turning. This is a typical these are typical component parameters that you look at when you're doing operation and doing analysis about operations on turning. We have a component to be held at the side by the spindle, the jaw, initial diameter, and then this is the final diameter that you are looking at, df. That's the depth of the cut. You can achieve this by multiple cuts and multiple passes. A cut is going to go down, a pass is going to be going sideways. So this is a pass. If you cut from here to here, you'll be feeding your tool going in this direction. That will be a pass. And then if you cut just from here to here. That's a depth of a cut, but this will be a total one that you are looking for. Let's see. Single point tool. Chip. A chip is just the material, waste material that comes from your block of material or raw material. It will be rotating at some V on the outside, but that's a rotational speed. Okay, the length, that is if you will be operating on this whole component. Otherwise, if we are saying you stop somewhere in the middle because of somewhere you will have your jaw holding up, your L is not going to be the same. We will give you the true length of the block. We will give you how far is your component and ask you how much material are you going to remove if you need the depth of whatever. That is a volume calculation. It shouldn't be a problematic calculation. Other related operations. So you have several operations that you can achieve on using turning. These are the operations. The first one, number A, facing, just making the end to look smooth. And taper turning, this is taper turning, you are making a cone. And then number C will be form turning. You have a shape that you are looking for and you will try to turn that. Number D is this one, these two are more like the same, but you see that the tool here has a surface contact. This one is a contour. You will be controlling this with feet. This one is controlled by the tool. The cutting edge of the tool will have a shape that you are looking for. Number E, chamfering. You have dealt with chamfering already in drawing, but basically just to kill the end sharp ends of your component. Here, F is cut off, but you actually want to cut this component here. Then you have G. This is used for threading, so you can make threads. Think of those threads that you find on big machines. That thread, when you perform it, you need to make it on both the big screws, even on the small ones actually. But you can use a lathe to operate that. So here you need to control the speed, and then you need to control the depth. Let's just go back a little bit. Here you can see that you almost have threads, but they are very, very fine to a point that they cannot even hold anything if you were to thread something on, to bolt something on this external threads. So actually that's the basic operation. With threads, you will perform the same turning. If you do the automatic feed and automatic speed and you are trying to perform a thread, you can, when you feed in this direction, your tool is going to follow the one contour line around the material. If you change the rotation and feed in the opposite direction, your tool is going to follow that same line going back. So if we have to speak about accuracy, I would say maybe it's not the same line if the accuracy is ultimate perfect tracing, but there's nothing as such in engineering. So we are talking about here something to acceptable accuracies and precisions. Then you have number H, boring. With boring you are inside the material. With the rest of them we are operating on the outside. With boring we are inside. So with boring you are in the inside, and then the rest of the operations that we dealt with, we were on coming from the outside. And then you have here, that is drilling on a lathe, inside, drilling into a hole. So this is rotated, this is stationary, therefore it's making a hole. And then you have either nulling. This is just to make a surface with a pattern that looks like this. So this one will also be rotating in this case. It's like making a dent on your material by forcing another hard material onto the surface. Let's continue. Engineering analysis that you will mostly be faced with for turning operations. Same things. In this analysis, we will be doing the feed rate, the time, material removal rate, the feeding rate, depth of a cut, final diameter, original diameter, cutting speed, rotational speed. All these things, they depend on each other to get kind of a final product. So if I told you you need to remove so much material in so much time, and this is the diameter and then this is the speed, then you can be able to tell me that with those parameters given, this will be the rate of removal. So that is MRR, material removal rate, and cutting time, depth, or for the one pass, I will also indicate that this is what I'm looking for. But I will also advise you to, because these are self-explanatory equations, I'll also recommend that you check in your textbook and read in details what they mean. But remember, you can use their units to kind of also get an idea what is happening behind them. That is with the equations that you're gonna need for turning. The rotational speed still is here. This might be confusing with the rotational speed that we used previously. Feed rate, time, the pass is L, material removal rate. All these equations are defined over here. And then we go further. We have an example that you can look at. I'm not going to touch this, but we have a memo in the same lecture slides. These slides are on ClickUp. Just go and do this example and see if you understand. We will discuss this example in the consultation session for this particular session. That is the approach and answer for that example. Work holding or component holding on the lathe. You have several types for holding your workpiece. The first one will be using a dock to mount, so your spindle will be somewhere at the back. The second one will be using a chuck or a jaw. Most of you will be familiar with this one. So you are using the jaw chuck to hold your piece. The other one, you use a collet. This is the spindle side, this is the spindle. This you can attach to the machine and remove it depending which one you want to use, and then you use that one. For jaw chuck, this one, after you have, if you want to use this one, you have, so this jaws can be linked, so they will move at the same rate going in and out, same position. Therefore, when they touch the circular component over here, this will also be touching same force, same position. Even on the one at the back, chuck will have a screw to actually force this to close up. Okay, let's see. For jaw chuck, however, some of them, most of them that I have seen, they have independent jaws. So this jaw and this jaw and this jaw and this jaw, they are independent. So you have to push this one, push this one, push this one, and push this one. And then you use something called a clock to make sure that you are on the center of rotation if you are looking for a center of rotation here. Other machines that you can find, tool room lathe, just go and find out what that means. It's going to be something that sticks in your head and then you won't forget it. Speed lathe, turret lathe, chuck lathe, automatic bar machine, numerical control lathe. This one is just the lathe in this age that we are in. A typical turning job. A typical turning job will involve several methods that we discussed all together to form the component that you are looking at. A typical job will just involve all those operations, or most of the operations, so that you can end up with this. So you apply them systematically. So after one, you go to the next one. After two, you go to the next one, and just like that. And when you are done, happy, you cut, take out your component, then you can go tap it or go further and thread it. Boring operation. Now, since I said boring is a little bit tricky, with boring you are using a lathe to make a hole. So, but this typically goes when you have bigger holes. So if you have a lathe, let's say this is a lathe, and then your lathe, this is your spindle, and then this is your jaw holding your component. This is your component here. This spindle rotates around this axis. Remember, this is circular. Just like that. So let's say with boring, you want to make a hole inside, say 30, let's say this is 30 centimeters, so 300 millimeters, and let's say your hole inside is about 25 centimeters, 250, somewhere there. It's big. You cannot find the drill that big. It's quite big. So 25 is big, therefore you want a cutting tool. A cutting tool, you mount it. You first make small hole. Of course, you first have to make a small hole with a drill. We are going to discuss drilling next. So you first make a small hole. You increase the hole up until maybe you get to 25 millimeters or 30 millimeters. That is, in actual sense, 30 millimeters, a hole of 30 millimeters diameter, something that big. Then you get your boring bar. Then you insert it now. It will go in. Let's say that was your drill. You have drilled a bigger hole that big. That's your hole right there. This one. 30. And you get your boring bar with a tool, cutting tool that does that. Then you start cutting. You move it out a bit by bit. As you perform your length of cut, you move it out, cut, move it out, cut, up until you can get to the size that you're looking for of 250. Okay, boring machines, you have different types. Here is a dog, as we previously spoke about it, and this is how you will hold it. This is a chuck or a jaw, and then that's your feeding. This is rotating, this is not rotating. Over here you have this one, and this is rotating. For this particular one, if you are rotating this outer component, that means your bar, your cutting tool is the one that is rotating, and you have your workpiece stationary. We will discuss milling as well. Milling describes an operation, let me just touch on that, where the component is stationary, it's feeding linearly, and the workpiece or the cutting tool is the one that is rotating. Even drilling, something like that. Most of the drilling operations involved a moving drill, and that will depend also on the size. I'm just thinking, but some of them you will have vice versa, where the drill is stationary and then the workpiece is rotating, like what we just saw with the operations around turning. That's your boring bar, cutting tool, and that is a teeth. You can change this. The reason for this, again, maybe just to mention it, is because when you change after this part is finished, you don't want to go throw the whole thing out. Therefore, manufacturing procedures, with the advancement of all these procedures, we have a way, just gonna unscrew and take out that and then put a new one. This is cheaper than the whole thing, so that is why you will have it like that. A vertical boring mill, so this one is the vertical one, but with this one you have a bait rotating which holds a part, but it's the same kind of thing. This is a spindle rotating, and then you have a component that is there, and then you have this all these tools coming in, feeding linearly. This will go in and will also go up. This one can go in and also to the side. And I think that is everything regarding the machining operation turning, and we will continue with the rest in the next two sessions, that is drilling and milling. So you can go and just have a look at videos around this machining procedures to be very helpful for you. Thank you very much for attending this session. We can discuss further at we will have a consultation session where we can discuss further for anything that you need clarification with. Thank you.